right, now we're going to talk about equations that have multiples of angles. So like a 2x, like a sine of 2x, or tangent of 1/2 x, or something like that. So let's say we want to solve sine 2x equals 1/2 for, let's do an interval here. So 0 degrees less than or equal to x less than or equal to 360 degrees. Okay, so let's start by figuring out how we can go about solving this equation here. So we can sort of ignore the 2x just for a hot second, and we're really just asking ourselves, where is sine? So for which angles is sine equal to 1/2? Okay, 1/2 is positive, and sine is positive in 2 quadrants. It's positive in quadrant 1 and quadrant 2. Let's make that a little bit better, because of our all students take calculus. Okay, so in quadrant 1, I'm going to have a triangle. In quadrant 2, I'm going to have a triangle. Sine is opposite over hypotenuse. So my opposite side is going to be 1. My hypotenuse is 2. And so that means my bottom side is going to be √3. Same over in quadrant 2. I'm going to have a 1, 2. Bottom side is going to be √3, except it's negative because I'm in quadrant 2. But that's not going to be as important. Okay, for the one in quadrant 1, my reference angle there is, this is 30, 60, 90. The angle's across from 1, so it's my 30 degrees. That means the reference angle over in quadrant 2 is also 30 degrees. So I'm going to use that to find the actual angle in quadrant 2 that I want, the green one. So I'm going to do 180 minus 30, that's 150 degrees. Okay, so I know that my input, my angle here, 2x, is going to be equal to 30 degrees and 150 degrees, and, you know, maybe some other angles too, but let's start with those ones. So I know 2x is 30 degrees and 2x is 150 degrees. Now, before I finish solving here, I want to think about if there's any more that are going to be in my interval. Okay, so now there's kind of 2 different ways to think about how to find all of the solutions in the interval, because it might not just be these 2. I might have more, and in fact, I do have more. Some textbooks will have, you don't have to write this down yet because I'm probably going to erase it, but some textbooks will write down what all solutions look like. So your plus 360k plus 360k. And then when you finish solving, continue to add all of that bit until you're outside of the interval. I personally prefer, I think it's a little bit easier, I actually change my interval in the very beginning. So if I want x by itself to go between 0 and 360, I want to figure out what do I want 2x to be going in between. And to figure that out, I can take this whole interval and I'm going to multiply it by 2 because I need to get a 2x inside. So how can I get a 2x? Just multiply that by 2. So I'm going to multiply everything by 2. 2 times 0 is still 0. 2 times 360 is 720. Okay, so I actually want, this is 2 full rotations that I am working in between, not just 1. Okay. So I have my 30 degrees, but I can also go another 360, so I can go a full rotation and then plus that extra 30. So a full 360 plus an extra 30, that's going to be 390. So I can also have a solution of 2x equals 390 degrees. And then I can do the same for 150. I can go a full rotation 360 plus an extra 150. So that's going to be, what is that, 510? So I also have 2x equals 510. Fix that. 510 degrees. And then you could always double check, can you go like 2 full rotations, 1, 2, and then 30? You're not going to be able to, because that's going to be 720 plus an extra 30. That's outside of my interval. That's bigger than 720. Okay, so these 4 are my only solutions. But I do have to like finish solving, so I still need to get x by itself. And all I'm going to do is divide everything by 2. So divide by 2, divide by 2. There's probably a much nicer way I could have written this, but I'm already here. Okay, so I get x is going to be equal to, so I have 15 degrees, I have 75 degrees, 390 divided by 2. Oh, what's that going to be? 9. Let's see. What is that? It's going to be 195. And then 510 divided by 2. That's going to be 255. Let me move this over. Those are all of my solutions. And you should always kind of double check, are all 4 of those numbers between 0 and 360? Yes, sir, they are. So we're good to go. Okay, let's do another example like this. Let's solve 2 times tangent of 1/2 x plus 1 equals 3 for, let's do the interval 0 less than x less than or equal to 2 pi. Okay, so now we're going to be working with some radians. Okay, let me rewrite my equation down here. So to start solving, I want to get that trig function by itself. So my first step is going to be to subtract 1 to both sides. And then my second step is going to be to divide by 2. So I have tangent of 1/2 x is equal to 1. So now I'm asking myself, where is tangent equal to 1? And as a matter of fact, why don't I just go ahead and change my interval right now? If I want, like the angle I'm looking at is 1/2 x. So I want to figure out where is 1/2 x ranging between. So I'm going to take this interval and I'm going to multiply it by 1/2. Okay, so I'm going to have 0 is less than or equal to 1/2 x is less than or equal to pi. Okay, so now I'm just looking at the interval from 0 to pi, and that might be helpful for me. Okay, so let me think about where tangent is going to be positive 1. Tangent, using our all students take calculus, is positive in quadrant 1 and in quadrant 3, but quadrant 3 is going to be bigger than a full pi, so I don't actually even care about quadrant 3. We're just going to ignore quadrant 3. So I just care about the 1 in quadrant 1. That's also why changing that interval I feel like is kind of helpful sometimes. Okay, so tangent is 1, or that's the same thing as 1 over 1. And tangent is opposite over adjacent. So my opposite side is 1, my adjacent side is also 1. That makes my hypotenuse square root 2, and this is a 45, 45, 90 triangle. Okay. I do want my answer in radians though, so I'm going to have my, not just x, but 1/2 x is going to be equal to 45 degrees is the same thing as pi over 4. So the last step to solve this, so I'm going to multiply everything by 2, which is the same thing as dividing by 1/2. So x is equal to 2 pi over 4, which is going to reduce to pi over 2. And that is actually my only solution for this problem. All right, so now that is it for this lesson 5.3. So what I want to do now is I actually want to do a few more examples from 5.2 that I didn't quite get to. So you don't necessarily have to watch this part. You can skip this part. But if you needed some more examples, here's some for you. In particular, I'm going to do those composite functions. So this is kind of like 5.2 examples. Okay. We'll do a couple here. Let's do, how about an inverse sine of I here, okay. Let's do, I don't even know, 3 pi over 4. Okay, so normally inverse sine and sine, they cancel out, and you're just left with whatever the input is. But this 3 pi over 4 is not in the range of the inverse sine. Okay, so we have to do a little bit of extra work. Okay, but all I really want to think about is I'm going to first draw out where 3 pi over 4 is. It's going to be in quadrant 2. So this right here is 3 pi over 4. Okay. That means the reference angle is just pi over 4. And I also know from my all students take calculus that sine is going to be positive in quadrant 2. So really I'm just asking myself between quadrants 1 and 4, so I'm ignoring quadrants 2 and 3 for inverse sine. Between quadrants 1 and 4, where is sine positive? And that's in quadrant 1. And what angle in quadrant 1 has a reference angle of pi over 4? Well, it's just pi over 4. So pi over 4 would actually be my final answer for this problem. So not 3 pi over 4, just pi over 4. So let's do another one like that. How about let's try an inverse cosine of what's one that's out of the range? How about a negative pi over 3? Sure. That's fine. Okay, negative pi over 3, that's in the range of inverse sine, but it's not in the range of inverse cosine, because cosine goes between 0 and pi. So it's not, my answer is not just negative pi over 3, so I need to figure out what it actually is. Let me first draw out where negative pi over 3 is. It's going to be in the 4th quadrant. It's just pi over 3 in the clockwise direction. So that has a reference angle of pi over 3, right? We can agree that the reference angle is just pi over 3. So I want to figure out between quadrants 1 and 2, because for inverse cosine, I'm going to ignore quadrants 3 and 4. Between quadrants, and then I also need to do my all students take calculus to figure out that cosine is positive in quadrant 4. So where else is cosine positive? Well, that happens in quadrant 1. So I need an angle in quadrant 1 with the same reference angle as negative pi over 3, and that's just pi over 3. Okay, so that one was actually kind of easy, like the one above. So pi over 3 is my final answer here. Let's do another cosine one. Maybe let's do it in, how about quadrant 3? So let's make it a 7 pi over 6. Yeah. Okay, so 7 pi over 6 is in quadrant 3. down here. That is my 7 pi over 6. It has a reference angle of just pi over 6 because this full guy is pi, which is 6 pi over 6. So to get a 7 pi over 6, I just need one more pi over 6. Okay. And then I also know that cosine is negative in quadrant 3. So between quadrants 1 and 2, where is cosine negative? Again, I ignore 3 and 4. Where is cosine negative? Well, it's negative in quadrant 2. So I have an angle in quadrant 2 with a reference angle of pi over 6. So be careful, pi over 6 is not our answer. This obtuse angle is our answer, which is going to be, it's a full 6 pi over 6. So 6 pi over 6 minus pi over 6. Well, that's 5 pi over 6. That's what this guy is. So 5 pi over 6 is your final answer for this one. Whatever. All right, that's pretty much it. Those are the complicated composite functions. If this number is in the range of your outside function, then you don't have to do all of this extra stuff. It's just going to be whatever that number is. These are the more complicated ones where you have to do a little bit extra because it's not in the range. Okay. All right, that's it for this video. Thank you all for watching.